Hi and welcome. This is a video on our section 4.2, which is Rolle's theorem and mean value theorem, and what these actually mean. So first and foremost, I'm going to say that I've highlighted probably the most important part of this theorem, that f has to be a continuous function on that closed interval. So it's going to still be on some closed interval, a to b for example. In both of these theorems, if they are not continuous through that interval, then we don't know that this theorem would actually hold true. So it has to be continuous on the closed interval. If it has discontinuity outside the interval, that's fine. And it has to be differentiable on that open interval. So let me show you in a picture how these two theorems are linked, and then I'll give them their names and talk about what they are. So let's say you have some blue curve. Let me highlight this function here blue so you can see what I'm talking about. So some function here, and notice we'll do that for both of them. Okay, and I'll even label the second one f of x because I don't believe it's labeled on there. Okay. So if we have some curve, and we know from the beginnings of Calc 1 that if I have 2 points along that curve, so here's one, that I can find the slope of that secant line. So I'll make the slope of that secant line, I'll make that red. So I can see that slope of that secant line. Again, if you have 2 points along any curve, you can find the average rate of change or the slope of that secant line. We've been able to do that forever. And how we do that, this should not be a new formula for you, is we find f of b minus f of a all over b minus a, and that is, right, the slope or average rate of change. That is the slope formula. F of b, which is y2, for example, minus y1 all over x2 minus x1. So this side would get me the slope of the secant line. Okay? And then, and I'm specifically going to just focus on this graph first here. So that would get me the slope of the secant line. And what this mean value theorem is going to guarantee for me is that if I'm continuous again throughout that interval from A to B, wherever I'm looking, so maybe I'm looking just from this point to this point, for example. Sorry, it disappeared. And maybe I know that I'm continuous and I'm differentiable, so then I can go ahead and make this statement. I know this will be guaranteed that there is one point in between A and B, so we call that the x value of C, where this tangent line that I drew, this tangent line is going to be parallel to the given secant line that we already found. And so I can see that, these lines are parallel, both this tangent line that is up above in orange or green and this big red slope of the secant line. I can see that these are parallel. And this is guaranteed by this mean value theorem, right? That you have an average rate of change and it will equal the instantaneous rate of change, right? So right here is an instantaneous rate of change. Right, at that one point. And so what we're basically saying is we know if the lines are parallel that their slopes are the same. So what I'm really saying overall here is that the slope of the secant line, where I'm using 2 points to develop that slope, is equal to the slope of that tangent line. So I just have to use my formula for slope, figure out what that's going to become numerically, and then set that equal to my first derivative. So let me show you how it looks in Rolle's theorem. This is really just a specified case, if you will, of that mean value theorem, because now if we look, and maybe this will make a little bit more sense showing it again, Here's my A, here's my B, for example. So I can find the slope of that secant line, right, between A and B. Again, there's my formula for the slope of the secant line. So I'll write that below it, M secant. But now, because my f of A is equal to f of B, I can see specifically that the slope of that secant line, the slope, right, M, or slope, is 0. F of A is going to be the same value as f of B, so that slope has a specific number now. That slope is 0. And the same premise occurs. If you are continuous throughout that interval, so you can draw from A to B without picking up your pencil, and you are differentiable throughout that interval from A to B, then there must be some point in here, C, where the slope is the same. Again, I'm guaranteeing that these two lines will be parallel. Well, if I knew my secant slope was 0, I'm really just looking for where is the slope of the tangent line 0. And again, f prime of C is the slope of the tangent line. So really, both of these theorems, if you look at their completion at the bottom, they both are going to say, where is the slope of the secant equal to the slope of the tangent? The only difference is in Rolle's theorem, Rolle's, that's the 0, right? So those slopes will specifically be 0. So let me show you how this is going to work. And I'm just going to use a polynomial so you can kind of understand the process for it and then go from there. So determine if Rolle's theorem can be applied. If it can, remember that's an if. If it can, find all C values in the open interval AB, so you want between A and B, not necessarily including the boundary, such that f prime of C is 0. They really didn't need to tell me f prime of C is 0, and I will show you why. So first thing I'm going to do is verify, is this function continuous? And again, you don't need it to be continuous all the time. You need this function just to be continuous on the interval that you are studying. So is this function continuous from 1 to 4? This is a parabola, so yes, this is. Let's say this is a function that has some vertical asymptote at 5. Well, I'm not really concerned as long as between 1 and 4 I'm continuous. And then I want to take a look at, am I differentiable? Which would go back to the discussion that we had previously on critical values. So if there's going to be a sharp turn, a kink, or a cusp, or something like that, a place where maybe my derivative does not exist, but my original does, this is just a parabola, so it doesn't have anything like that. So I am continuous, I am differentiable, so I can apply Rolle's theorem. So here I go. I'm going to just find what is f of 1, and I'm going to find what is f of 4. So I don't need to necessarily see you do this by hand, but that is entirely up to you. If the function is a little bit more complicated, I would highly just recommend going to your graphing calculator. Again, this is entirely up to you. If you have your calculator ready, you can certainly use it. If you don't worry about it. And if you do want to do this on your calculator, you would go to your y equals. I would type in my function. And again, I'm just trying to alleviate some of the more complicated functions you might not want to calculate by hand. This one I certainly could. It's not going to take me that much effort. But and then remember, if you go to your second table set, we should all have our table set to independent variable. Go over to ask, because that way when I go back to my table, it's waiting for me to type in x values, and I can say evaluate when x is 1 and evaluate when x is 4, and I don't have to do that work myself. So these are both 0. Okay. That has nothing to do with the 0 of the original problem. That's just a coincidence here. So then what I'm going to do is just find the slope. So if you want to write it as a point, you can. This is the point 1, 0. This is the point 4, 0. And I can find the slope of that secant line. So the slope of the secant line would be 0 minus 0 over 4 minus 1, or 0. So whatever that secant slope is, this is true for Rolle's theorem or mean value theorem. It's just Rolle's theorem, that slope is specifically going to be 0. Mean value theorem, it's going to be some other number. So slope of the secant line is 0. I know then this will guarantee that somewhere in this interval there is a parallel tangent line. So tangent line, here's my calculus, okay? So f prime, right, will give me the slope of the tangent line at any x value. So I'll do the first derivative. And then again, f prime of x is the slope of the tangent line, right? So I'm basically saying, where is the slope of the tangent line equal to the slope of the secant line? I have a numerical value now for the slope of the secant line. I know the slope of the secant line is 0. So I'm going to set this equation for the slope of the tangent line equal to 0 and solve. And I keep this as x, so bear with me for a second. So you can write it as 5/2 or 2.5, okay? And the reason I keep it as x for now is because you might have multiple x values. I only want c to be in that interval, okay? So if I have multiple x values to choose from, the only true c value is the one that is in between my given interval. And that's the x value, or c value in this case, between a and b that's going to guarantee I have that parallel slope. Okay, let's do another one. So, determine whether mean value theorem can be applied. If so, find all values of c in the open interval ab such that, and really, again, I don't know that this needs to be given to you because this is just saying slope of the secant, right, equals slope of the tangent. So here's slope of the tangent equals slope of the secant line. Okay, given this function, so first thing I'm going to do is I'm going to rewrite this function. I don't think you should have to use product rule here, so it's x cubed minus x squared minus 2x, and here's my given interval, -1 to 1. So again, I want to check two key things. Am I continuous? And am I differentiable? Again, only in the interval that I was given. -1 to 1. Well, again, this is polynomial, so I would say yes to both, so I can go ahead and find the c value where this is going to occur. So I'm going to find the slope, and again, I don't need to see your calculations. I think sometimes it is faster to do it on your own computation, you know, on side work or in your head, but I don't want to screw up that part, right, for the problem. So I'm going to go to my calculator, and I'm going to type in this function into y equals. Okay, so here I've got my function in there, and now I will go back to my table and take a look. And now I want different values. So if I just hit delete for each one, then it'll take off whatever I have in there. If it doesn't bother you that you have old values in there, you can just arrow down to a free row and type in your x values. So the first x value that I want to calculate would be -1, and the second x value I want to calculate is x equals 1. So, oops, I didn't remember what they were. So -1, 0 is going to be one of them, and 1, -2. So -1, 0, and 1, -2. Okay, so I have my points, so I'm going to calculate the average rate of change, or the slope of the secant line, which is good old-fashioned slope. So y2, so -2 minus 0 over 1 minus -1. So I should get a slope of -1. Again, that's the slope of my secant line. So let's now find the slope of the tangent line. So here's derivative work. So I'll find my first derivative, which again is just power rule. So you should be finding these derivatives to not be too terrible. This is again the slope of the tangent line for any x value, right? And I'm saying the slope of the tangent line is equal to the slope of the secant line. And I have a numerical value for the slope of the secant line, so I'm going to put that in. So this would be -1 equals that quadratic. And I purposely picked this one because sometimes when we solve this quadratic, we try to factor the right-hand side as it sits right now. Please make sure all of your quadratics equal 0 if you are using quadratic formula or factoring. So I'll add 1 over here, so that will be a -1. And then I can factor this, or you can use quadratic formula if you so choose. And I needed to add to -2x, so I'll do -3 plus 1. Okay, so I have two answers for x here. If I solve that using the zero product property, I would get -1/3. And if I solve this one using the zero product property, I would get x equals 1. And this is why I leave them x until I'm all the way done. You want your answer to be in between that interval. So I want this answer to be in between -1 and 1. I was trying to highlight that for you. So if it's in between -1 and 1, I do not want to use the ones that are actually on the border. So I'm not going to use that one. So this value of x equals 1 included. So I'm going to scratch that one out, and I'm only going to include this c of -1/3 because that is the one that is in between -1 and 1. So I hope you found this video helpful, and again I will leave you with that visual of what mean value theorem and Rolle's theorem really are. So again, you are just guaranteeing the existence of a tangent line, so where it crosses your curve at one point, right, your instantaneous rate of change, where that tangent line is parallel to a secant line. So you're going to be given 2 points. Find the slope between those 2 points, that's your slope of your secant line, and set that equal to your first derivative, which will give you your tangent line at any x value. And then you can solve where does that slope equal that slope. I hope you found this helpful.